Hi and good day, madam. I'm Siti Atifah binti Shoiful Anuar and my metric number is 251362365. I will begin the presentation with introduction. Power quality enhancement is crucial in modern electrical systems due to sensitive electronics and the integration of renewable energy sources like solar, which introduce fluctuation and harmonic distortions. Maintaining high power quality is vital in real-world application for several reasons. It ensures the reliability and protection of sensitive equipment from damage and malfunction caused by states, swells, and harmonic. It facilitates grid stability and seamless integration of intermittent renewable energy sources, helping meet sustainability goals, and it improves energy efficiency and lead to significant cost saving by mitigating energy loss and avoiding utility penalty associated with poor power factors and harmonic current.
Good day to Madam Kumuta. This is Choo Zhan Zao, and I'm going to present about the literature review of the assignment. Firstly, I would like to introduce the power quality problems. Power quality problems such as harmonic distortion and voltage fluctuation can contribute to unwanted consequences such as system overheating and instability. So to solve these problems, active filters are introduced and utilized in active power filters to remove undesired portions of a signal. So there are four types of active filters. The first one is the active low-pass filter, which allows low-frequency components to pass through but rejects those with frequencies higher than the critical frequency. The second one is the active high-pass filter, which allows high-frequency components to pass through but rejects the low-frequency components that are lower than the critical frequency. The third one is the active bandpass filter, which only allows one band of frequencies within the bandwidth to pass through, but rejecting all other frequencies that fall outside this specific band. The fourth one is the active band stop filter, which rejects one band of frequencies within the bandwidth, and all other frequencies that are outside the specific band are allowed to pass through. Next, I would like to present the control strategies for active power filters. The first one is the instantaneous PQ strategies, which detects DC and AC components by measuring the real and imaginary powers in the system. This strategy offers fast dynamic response and is widely applied in three-phase systems. The second one is the synchronous reference frame (SRF) strategy, in which the load current signals are transformed into a rotating reference frame with the fundamental angular frequency. In this strategy, the fundamental current components appear as DC components, while the harmonic components manifest as AC signals. The third strategy is the discrete or fast Fourier transform, which separates the harmonic components of the capture voltage or current signal by eliminating fundamental components. However, time must elapse to gather sufficient samples and process the transform, since this is not a real-time method. So here are the summary of previous researchers. Previous researchers has employed different approaches to solving power quality problems in grid-connected and standalone solar PV systems. Some of the research utilize passive filters, while others employ active filters as an approach. Passive filters don't need an external power supply and have no bandwidth limitations, allowing them to handle larger current or voltage levels. However, they cannot produce gain due to the lack of amplifying elements, and tuning inductors can be time-consuming and costly. Active filters require external power for their amplifying elements and are limited by active components. However, they can provide the desired gain, offer high selectivity, and are cost-effective due to the availability of economical op-amps. Therefore, the active filter approach has been chosen for this research. That's all for my presentation. I will pass this to the next member.
Okay, so for the methodology part, explain the process used to design and analyze an active power filter for a standalone PV system. The system was modeled and simulated using LT-SPICE. For the approach includes system modeling based on the PV and nonlinear load structure, active filter design and component calculation, closed-loop control strategy, simulation, and result. For block diagram, this block diagram shows the overall structure of the standalone PV system with an active power filter. The PV array supplies power through the inverter to a nonlinear load. Due to nonlinear load behavior, harmonic distortion occurs at the point of common coupling, or PCC. To improve power quality, an active power filter is connected at the PCC. The filter senses the PCC voltage, processes it through a control circuit, and injects a compensating signal to reduce harmonics and stabilize the output voltage. For the circuit was implemented using LT-SPICE. The PV inverter output was modeled as an AC voltage source To simulate nonlinear load effects, harmonic voltage source at 150 Hz and 250 Hz were added, along with a 10 kHz switching component. Resistors and inductors were used to represent line and load impedance. This distorted voltage was then applied to the active low-pass filter circuit to analyze its harmonic suppression performance. And then for the component selection and calculation, this slide showed the component selection for the active filter. The cutoff frequency was designed using the equation Fc equals 1 over 2 pi Rc. By selecting a resistor value of 20 kilo ohms and a capacitor value of 39.789 nanofarads, the cutoff frequency is approximately 20 Hz. This allows the 50 Hz fundamental component to pass while attenuating harmonic frequencies and switching noise. For simulation setup and evaluation, the system was simulated using transient analysis in LT-SPICE. The simulation time was set to 0.1 seconds with a time step of 0.005 seconds to observe steady state behavior. Voltage waveform were monitored at the input and output of the filter. The results show that the output voltage waveform is smoother and closer to pure sinusoidal shape compared to the distorted input, which confirms the effectiveness of the active power filter.
Good morning, madam. I'm Lee Jiang. I am going to present the result of project. This is our simulation waveform. From the waveform, there are three types of curve with different color. The green curve refers to the input voltage, and the blue one is output voltage, and the last one, the red one, represented the voltage after the resistor one. Next, I will talk about the system performance and efficiency analysis. The 7 kilo pass filter demonstrates high effectiveness in harmonic extraction as evidenced by the elimination of 10 kHz switching ripples in the blow out trace. A critical performance limitation is the saturation of the LM op amp because the input signal 325 watts vastly exceeds the DC real 15 watt and the output is forced to its maximum swing limits, result in no sinusoidal pulse observed in the simulation. Under current saturation condition, the system efficiency is compromised. The op-amp operates in its nonlinear saturation region, leading to significant output distortion and energy dissipation as hit within the IC radar, providing a pure reference signal. At last, I will summary the simulation metric for our assignment. In first, the input peak voltage is 325 volt and the input fundamental frequency 50 Hz and op-amp superior VCC or VCE plus minus 15 volt and resistor value R1 and R2 is 30 kHz and capacitor value is 39.789 nanofarad and output voltage is 28 volt tripled.
Hai, Assalamualaikum warahmatullahi wabarakatuh and good evening. My name is Nur Balqis binti Mohd Nizam, matrix number 251362352. This is a comparison part for theoretical design and simulated result. First, for cutoff frequency FC parameter, in our design based on resistor value and capacitor value, the calculated FC is 200 Hz. While in our simulation, the blue output trace shows that the 10 kHz switching noise and higher order harmonics are successfully attenuated. For input signal magnitude parameter, represent the required 230 VRMS for 3000 watt system, while in our simulation, the green trace Vin correctly shows a peak of 325 volt with superimposed noise. Next, for output voltage level parameter, in our design we expect a clean 50 Hz reference signal proportional to the input, but our output is severely clipped and limit to approximately plus minus 14 volt in our simulation. Lastly, for waveform quality, in our theoretical design, we expect a pure smooth sinusoidal wave for the inverter's closed loop control. But in our simulation, the high frequency fuzziness is removed, but the result is a series of all due to clipping. Next, this is waveform and op-amp saturation analysis. First, for input-output discrepancy, the 230 VRMS, which is 325 Vpeak, input signal significantly exceeds the operational range of the control stage. Next, for op-amp clipping, output VL is severely clipped at 14 volt because the LM741 is limited by its DC supply rails. For saturation trigger, physical constraints of the op-amp prevent it from processing the high voltage peaks, which is indicating the filtering logic is sound but the voltage level is unsafe. Lastly, required mitigation, a step down stage, which is potential divider or transformer, is essential to scale the signal before it enters the active filter. This is the last part for discussion. For design advantages and reliability, our circuit design offers high input and low output impedance, preventing loading and effects and ensuring a sharp 200 Hz cutoff by using silent key topology. Next, for signal integrity, our design successfully isolates the 50 Hz fundamental frequency with minimal phase shift for precise closed-loop control. Our design also proposes hardware improvement based on voltage scaling that can eliminate signal clipping and protect the circuitry. For precision components, our design have 1% tolerance resistor or capacitors to prevent frequency drift. Based on high slew rate of amps, we can replacing LM741 with TL082 or OPA2134 for better tracking of higher order harmonics. Lastly, our design ensure the system meets IEEE, which is the standard compliance for standalone PV environments.
Last but not least, for the conclusion, the report concludes that the successful design and simulation of a control stage for a shunt active power filter utilizing a second-order silent key LPF effectively suppress high-frequency harmonics by targeting a 10 kHz switching frequency and establishing a 200 Hz cut-off frequency to isolate the fundamental power component. Despite the simulation proving the filter efficiency, the results highlight that physical limitations relate to using low voltage op-amp with high voltage AC source. Future improvement will focus on implementing signal scaling techniques to prevent op-amp saturation, ultimately providing a clean sinusoidal reference signal for the 3000 WPV inverter system.